for a tough probability question from the methods course. We know that Arnold is a triathlete. Now, the chances of improving swimming is 2/5 of a chance. The chances of improving cycling is 1/3, and the chances of improving running is 1/8. And all of these three components are independent in terms of their performance, and the other two components are independent from them. We have a look at part B. It says, during the first triathlon, Arnold improves his cycling. Okay. Find the probability that Arnold also improves his PB and at least one of the other cycling or running components. At least one, so it could be both as well. Now, this is a really big key here, our independent components, all right? So we can't forget that. We know that we're going to have to use that somewhere, so we'll come back to that. We have a look at the first sentence here. It says that Arnold improves in cycling. And then it goes on to say, what's the probability that he improves in something else as well? So we want to find whether they improve in running or cycling, or both of them, given that they already improve in swimming. So if we write that as equation, the probability of cycling and running, given that they improve in swimming, plus the probability of cycling and not running, given that they improve swimming. It's important that you do this not running part, because if you just do cycling and swimming, you're assuming that this experiment only has two factors, being cycling and swimming, but it doesn't. It has three. So you have to include all those three in your working out. So if it's just cycling that improves, that means you'll find the probability of cycling and running not improving. And then finally, the probability of running improving, but cycling not improving, given that swimming already improves. Now, let me just point this out to you. These events are independent. That's important, because let's say if we use this as an example, what we're going to end up doing, we find the probability of both and S divided by S, right? But in this case, it's actually going to be, because they're independent, it's just going to be C times R times S divided by S. Now the S's cancel out, just leaving C times R. All right? And the only reason why this works is the key word independent, because we know that the probability of A and B is just A times B. So this is why we get to this stage. Now, if that's the case, let's go back a few steps and get rid of all of this. We don't even need to consider swimming. The answer is just probability of cycling and running plus the probability of cycling and not running plus the probability of running and not cycling. All right, so let's put some values in. We'll do that on the next page. Okay, so we know that cycling equals 1/3 and running equals 1/8. So let's just do them both first. Remember, they're independent, so if they both occur together, we just multiply those two together. So we go 1/3 times 1/8. So that's cycling and running. If we just do cycling, then we're going to go 1/3 times 7/8, because we don't improve in running. And then if we do just running, we're going to go 1/8 times 2/3 for cycling, because we don't improve in cycling. So therefore we've got 1/24. Now I can't even read my own handwriting. Then we're going to go 7/24. And then we're going to go 2/24, which equals 10/24, which is 5/12. All right. It's important to recognise the keys that they give you. Methods is a subject where there's many different solutions for one answer, and if they tell you that something is independent and they tell you something is conditional, then use those to your advantage to find the quickest way to answer your questions. Hope that helps.